The universe is 13.8 billion years old. It contains 2 trillion galaxies, and inside each of those galaxies are hundreds of billions of stars. With planets orbiting nearly all of those stars, the raw mathematical probability of biology emerging somewhere in that expanse is staggering. There are almost incomprehensibly large numbers of chances for life to begin. Yet, across the entire history of human observation, we have documented 0 confirmed signals, 0 visits, and 0 pieces of extraterrestrial engineering. Not a single artifact. When you account for the sheer scale of space and the billions of years available for life to develop, that total lack of contact ceases to be peaceful. It becomes a mathematical contradiction. To understand exactly how deep that contradiction goes, we have to look at a conversation that took place in the summer of 1950 among researchers at the Los Alamos National Laboratory. Physicist Enrico Fermi was discussing the mechanics of faster-than-light travel with his colleagues when he paused to ask a strictly numerical question: where is everybody? This timeline compares the 13 billion-year age of the Milky Way against the time it takes for a civilization to expand. If an intelligent species emerged just 1 million years before us and traveled at standard speeds, they'd have enough time to physically reach every star. They wouldn't need exotic technology. Simple, self-replicating probes could colonize the entire galactic disk. The math dictates that we shouldn't have to search for signs of life. Our solar system should already be thoroughly overrun by their infrastructure. The fact that it isn't is the core of the Fermi Paradox. In 1961, astronomer Frank Drake attempted to organize this chaos into a formal structure. He took Fermi's broad question and broke it down into specific requirements. This diagram illustrates Drake's framework as a chain of multiplying fractions. To arrive at a detectable civilization, you have to multiply the rate of star formation, the fraction of those stars with planets, the planets that can support life, the ones where life actually starts, where it becomes intelligent, where it develops broadcasting technology, and finally, how long that civilization survives. Through modern astronomy, we have solid data for those first few variables. We know planets are incredibly common, but the later biological and societal steps remain entirely blank. The equation cannot give us a definitive number of alien races. What it does is highlight exactly where human knowledge stops, proving that somewhere in that chain a massive failure must be occurring. One logical explanation targets the early variables in that chain. The rare Earth hypothesis suggests that the leap to complex, intelligent life is exceptionally uncommon. Earth relies on a highly specific set of stabilizing conditions. We have a heavy moon that regulates our tilt, a massive gas giant like Jupiter that intercepts incoming asteroids, and a magnetic field shielding our atmosphere. Without that exact combination, biology might never survive long enough to evolve intelligence. This funnel graphic models a much darker alternative, known as the Great Filter. This theory argues that somewhere along the evolutionary path, there is a specific, nearly impossible hurdle that prevents civilizations from advancing any further. If that filter is behind us, perhaps the jump from single-celled organisms to complex animals, then humanity has already survived a cosmic lottery. We beat the odds, which means we are likely alone in the galaxy. But if the filter is ahead of us, civilizations reliably figure out spaceflight and then reliably destroy themselves before leaving their home systems. Whether through nuclear war, engineered pathogens, or artificial intelligence, the progress inevitably collapses. The Great Filter leaves us with a stark choice. Our survival to this point is either an absolute fluke of chemistry, or we are steadily marching toward the same wall that destroyed everyone else. Other scientists look past biology and suggest behavioral explanations for the silence. The zoo hypothesis proposes that advanced species are fully aware of us, but they treat Earth like an isolated nature preserve, deliberately withholding contact until we cross a certain threshold. Then there is an explanation that relies entirely on fear. It is known as the dark forest theory. This diagram outlines the core game theory of that concept. Because it is impossible to know the true intentions of a distant alien species, assuming they are hostile is the only logical way to survive. Broadcasting your location isn't a greeting, it is an invitation to be destroyed. The resulting survival strategy is harsh. The safest move is absolute silence. If another species reveals their position, the safest response is preemptive elimination. Under this framework, the galaxy is not empty. It is densely packed with civilizations that are heavily armed, deeply paranoid, and holding their breath in the dark. While those theories exist in the abstract, modern science continues to test the sky. Organizations like the SETI Institute run massive radio telescope surveys, listening for any sign of artificial transmission. At the same time, observational missions like Kepler and TESS have mapped our surrounding star systems. They have confirmed that thousands of exoplanets exist, with many sitting squarely in habitable zones. The raw materials for life are demonstrably everywhere. Yet, despite mapping the stars and scanning the frequencies, the empirical reality has not changed. We still lack a single confirmed biosignature. The silence persists. It leaves us to face the implications of our own data. Either we are a staggeringly rare chemical accident, we are doomed to self-destruction, or we are surrounded by things we cannot see. Until we find definitive proof of biology beyond our atmosphere, the question asked in a Los Alamos cafeteria remains the most unsettling mystery in science. The universe is ancient, it is vast, and entirely capable of hosting life. So where is everybody?